right, so one of the aspects is that I think I just made a huge leap to say like, yeah, I went from, every particle on here wants to spin a circle, and then I just said, Milky Way, and then our solar system, and then our, you know what I mean? But we don't want to break this down, because even that's Newtonian mechanics. Like, even if you do move this, like even the universe is still Newtonian. We can see a solar system, spinning. We can see the Milky Way turning. That's just like I'm over here and I got over here and it took some time. Okay, so but we want to know why every molecule on this plate really wants to do that. See, we understand that this plate, is all fused together, and every molecule is going to be basically doing the same thing. But this is cool because now I think we're into like an idea that this is actually a fluid. Like you're taking that leap into fluid mechanics, which is still Newtonian mechanics. Just because like a water swirling in an eddy, don't mean it's a quantum eddy. Like, hey, I'm stuck in a quantum eddy. No. You're still stuck in a Newtonian eddy. But it's just interesting going from a position, we thought the plate was here and then it's over there. But if anything weird happens, especially you're just like, you can't quantify it by time. You can't be like, well, I took these snapshots and it don't add up. And then you're in kind of the quantum realm. But let's take a look at just one of these particles. I don't know where on this plate. This is just kind of like a work in progress. But so what we do know is that the center of this plate, if it rolls from here, like one full revolution, goes from there to there. That's kind of the distance that we want. So let's say you have a particle here. It's already going to go it's starting down here. This particle down here is also going to go from here to here. But guess what? It's going to go up too. So it's got to go up, over, and then down, in a huge sense. But, even though it's kind of just a normal curve, it's going to go up and then down. You know what I mean? Just like a big old curve like that. But even that's too much motion. It went too far. You know what I mean? You're like, how'd you get there? It'd be like the guy that you saw, at the coffee shop over here, and then 2 weeks later you saw him at the grocery store. You're just like, well, they could have took a trip around the world, and then you saw him at the grocery store 2 weeks later. So they did like a circular motion around the world, and then you saw him. You know what I mean? But it added up to be the same. You know what I mean? So even here, like every time we Newtonianly move this plate, even like the frames I'm capturing, probably 60 frames a second. If I go frame by frame, the plate's here, and now guess what? The plate's here. So like the plate's here, and now the plate's here. That small molecule is now like up. You know what I mean? And then, like I said, anything up, that's an extra, because we're just going from there all the way over there. So to get this molecule to not go up, if the only thing we can do is spin this molecule, well, guess what? We have to like unwind it. So that's kind of like what I was getting at, of like this thing wants to spin. Like if a molecule is trapped where it can only, even though you threw it up here and then you went down, if it has to, okay, so now how the world are you going to spin a molecule, and do that? But we already proved it. We showed Aristotle's plate with the second plate, but we put it on bearings. So now when that plate moves across, well, if it's friction on friction, that little thing is going to move way faster, because it's a small circle and it's got to go like the same distance as the big circle. So we all understand that. Okay, so why can't you understand that, like, hey, you just take a small, like this is where like integral calculus, you're just like, you have to go, oh, okay, like I get it. Like, anyway. You take a small little circle here, and you're like, yeah, and then you, this is perfect. So check this out. Okay, if you're, This is 21st century Aristotle's plate, or whatever they call it, Aristotle's wheel. Aristotle's circle, I don't know. But okay, you can imagine a circle here, and then you put it on a bearings. I don't know why I struggle with finding out that name. But and then you roll the plate across. This plate gets rolled across this table, and that smaller plate on bearings gets rolled across the shelf. And that wheel really moves. Okay, now you just do it. You draw a small little circle here. So you know this point right here is going to do that, like, I forget the name, cycloidic or like I don't know. It's a funny name. It's the name for this line. You go from here and you go up and then you go down. See how that's just a big old arc? Okay, and you can watch those videos. Those videos are a dime a dozen. Okay, but now you can take a small little circle, cut that little circle of a plate out. Because guess what? That small circle of a plate, well, it's gonna run on that line too. You know, so that line we're gonna turn into its own shelf. And now, see, now I think you're like, light bulb's on. Whoa. Because I get this, how you take a small circle, put it on some bearings, have that second shelf. That circle's gonna spin real fast. Well, now, this point does that little, like that, whatever it's called. I don't know. I haven't watched the video over and over again. But anyway, so, but yeah, you make your shelf look like that. And then guess what? You cut out a little circle, and then you have that on bearings. And then that's going to be up against that shelf that looks like that. And guess what? The second you start to turn this thing, that little circle is going to go a mile a minute. It's just going to spin like hell. It's going to be like, whoa, what the hell did you do to me? And, you know, and honestly, you take that circle and you draw like the smaller it gets on that same shelf. Well, guess what? That little freaking circle is just going to spin miles a minute. You know what I mean? And we're not even talking miles a minute. You draw that little circle down to a little atom, an atom of a plate, and then put it on bearings and make it go that same arc. Well, guess what? I mean, that thing might be cooking. You know what I mean? It's just like, well, what's the limit? It's probably the speed of light. You know what I mean? I mean, then you get into concepts. But even there, you're just like, whoa, you just blew my mind. Because I understood this. Like, yeah, that plate moved twice as fast. Okay, well, even make that plate. Make that plate super small. You know what I mean? And then put it on that same flat shelf. And then put it on bearings. You do this, how fast that plate moving? Like, whoa, really fast. And then just make it like an atom-sized little circle on bearings. Take that plate and do this. And that other one's on a shelf. And guess what? That little atom is going to go fast as hell. You know what I mean? Sky's the limit. And now, like anytime you get to a limit, or like a little quantum packet where you can't slice things up no more, then you're into the quantum realm. You know what I mean? Or like you can understand quantum mechanics a little easier. So there you have it. You have like a microscopic circle of an atom right next to the part of the plate that's on the surface. And then you put it on bearings. And then you make that shelf look like that arc. And you can take anything. Like see how this is a straight line? Well, we did that one. We just did it friggin' fast. You know what I mean? And then we took the molecule right there. Oh, shoot. I got to get this, but maybe it's just spam. Hi, this is David. Oh, great. Yeah, let me holler. Just a second. Hey, Mom. I think she's downstairs. Yeah, okay, cool. She's having hot outside. Okay, I'm back. But I think you get it now. Because we just did the center of the plate, tiny, tiny particle, little wheel of an atom on bearings. It's going to spin on that flat shelf going across. And then we pick the particle right here. It's going to do that up and down. And then we make a second shelf. And then we chisel out a small little atom of a particle, put it on some bearings, and have it spin on that shelf. You know what I mean? Friggin' fast. You know what I mean? Light speed. Probably like the speed of an atom. Like how fast does an atom spin? Well, that fast. You know what I mean? That fast. But you get down to that, like, well, how fast does an atom spin? And is there a limit? And that's a great question. Because you're just like, well, I know the speed of light is like a particle goes from here to here. But we know, like, even a particle moving at the speed of light is like a circle. And we know that particle spins. I mean, is the particle spinning this way, where it's like going forward and then going back and then going forward? It don't matter whether it's going this way or that way, or if it's spinning like this. But we know a particle goes from the speed of light from here to there. But a particle is a circle. So you actually know parts of that particle are going faster than the speed of light. You know what I mean? And then you get into like, well, if you actually do that, what's the guy? I know, the guy that slices the apple pie. Carl Sagan. You know, if you take that Carl Sagan circular atom, you know, and it's like spinning this way, tumbling head over heels, you take any point on that atom, well, it can do the same thing. You know, it can probably move infinitely fast. But anyway, back to it. That's a separate video. But back to our plate. The other thing from Aristotle's circle is that you know that this point goes up and down. This point in the middle just goes across. And then like this point, like right here, well, let's follow it. It starts right here and then goes up and then down. But I mean, if you did two circles, you know, yeah, it would just go like whoop. It's like just subdued. So you either have the center or like the top to bottom is just very sharp. And then any one in the middle is like woo, just like a, you know, going with the flow. So all the other ones are just kind of going with the flow. But you can do that same thing. Let's pick a molecule right here, draw that, build that going with the flow shelf, take that atom, draw a circle, you know, detach it, put some bearings on it, and then have this plate spin once, but that little atom is also going to spin fast as hell. Now, out of all those, if we get down to just one atom, well, is this atom going to spin, I'll just say, this atom is probably going to spin slower because it's only going from here to here. But this atom, if you built the shelf that looks like this, well, this atom wants to spin hella fast. You know what I mean? So that's the idea. And I think you get it. And every single atom on this plate wants to just do that. It wants to probably like spin in that direction. So you just pick whatever atom, do whatever circle, and that circle could be a big circle in the center. You know what I mean? It could be if you're going off to the side, you probably have to do a smaller circle. But again, you're going to build that same shelf. Even that smaller circle is going to have some sort of bottom, and if you follow that small circle, it'll have to go over the shelf. So you'd probably pick a circle of any size anywhere on this, and then figure out what shelf you need to build, and then when you spin this once, that other circle that you cut out, put on bearings, is going to spin faster. And I bet definitionally, if you take any circle inside this plate, those circles are going to spin faster when you spin this outer circle. Now, if this plate was a part of a huge plate, you know what I mean, that was somewhere in that plate, and then this was on the bearing, you spin that big plate once, well, guess what? This is the plate that's going to spin faster, or like fast as hell. But there you go. So every little atom on here wants to spin faster than the plate. But it can't because it's all glued together. But perfect. I think we got to a stopping point. You're like, whoa, I didn't know that. I didn't know if you spun a plate, every little atom's like, dude, I want to spin, but I can't because I'm glued to this plate. So that's slippage. So that's where, and I really do think there's a quantum element, because you're just like, well, it can't. So somehow, like it's got to go from you know, it takes time, you know what I mean? Like your friend that you saw at the coffee shop and then at the grocery store, well, he went around the world and then you saw him at the grocery store. You know what I mean? Like, and that's where it gets down to frames per second. Like if we have the fastest camera, slow-mo guys, and are just looking at this, and you're just like, well, we moved the plate just to there. You know what I mean? Well, what did we see that molecule do? Well, it's just like, how did that molecule go from here just to that next position? Like, you slice up time, like slicey enough, well, you get into a realm where it shouldn't have moved